Jerry, I think I'll hand it over to David.
Oh, well, thank you. Well, welcome everyone to Preventing 10 Common Security Mistakes in the Mean Stack. Brief introduction, who am I? I'm David Bohannon. I'm a security consultant with Synopsys, based out of Atlanta. And I've spent the last year or so working with mean stack applications. So more specifically, mining vulnerabilities in these technologies, frameworks, and plugins, and then converting those vulnerabilities into triggers for a static analysis engine. So who is this talk intended for? Well, really for both developers and security professionals. And what can you expect from this talk? Well, so I designed the talk with the assumption that the audience has a basic understanding of Mongo, Express, Angular, and Node.js. So that allows us to forego a lot of the basic introduction to these technologies and rather focus on the actual vulnerabilities and common mistakes. Now, what makes these common mistakes? Many of them are the result of using these components in their default configuration, or they're simply the result of mistakes that are easily implemented by developers. So I've also created a intentionally vulnerable mean stack application that we'll use to demonstrate these problems, these issues, as well as the solution. So we'll show you not only how to exploit these mistakes, but also how to fix them. We've got 10 different things we're going to talk about in the course of about 40 minutes, so we're going to be moving pretty quickly. So without any further introduction, hang on, and here we go. So the first part of the technology stack we're going to pick on is MongoDB. So MongoDB is a NoSQL database. So it doesn't have a concept of a structured query language. And as I'm sure everyone knows, historically one of the big problems with a SQL database is SQL injection. So we have some sort of untrusted input that's appended to our query statement that allows a malicious user to alter that query, drop databases, add rows, things like that. So the question is, does NoSQL mean no injection? Well, the answer is no. MongoDB has a concept of query selector operators. And these are all operators that start with a $sign. $GT means greater than, $NE for not equal to, and $not for negation. And if an attacker can inject these queries or these query selector operators into the query, they can alter the logic of that query. So, for example, let's look at this query, this find one, and essentially what this is doing is doing a lookup for a username that matches our variable user and a password that matches our variable pass. So it's part of our authentication flow. And what happens if the user inputs this? So it's the object where the user is admin and the password is the object not equal to null. Well, the result is we're looking for the password where the username, or the entry where the username is admin and the password is the object not equal to null, which is always going to return true, which is going to allow us to authenticate to the application without actually having a valid admin credentials. So this is great, but how do we do it? How do we inject these nested operators like this? Well, Express helps us out. So if we're using the mean stack, we have our Mongo database. We're also expected to have an Express server. And when Express sees these nested URL encoded parameters in our input, it's going to automatically parse them for us. So what happens is in either our get URI or our simple post form, the URL encoded parameter pass bracket $NE equals is actually going to be translated to the password is the value of the object $NE or not equal to null. So this allows us to again inject our query operators into our find one statement and alter the logic of this operation. So one way that we can fix this is to simply cast our input to a string. So what we end up with is a result that's looking for the username, or a query that's looking for the username admin and the password that's the string representation bracket $NE :null. So that's one way that we can prevent users from injecting our query selectors. The other option is to simply sanitize our parameters that begin with $keys. So we can do this manually, or we can use one of the off-the-shelf packages that'll do this for us, right? So if an attacker tries to inject these query operators, it's going to strip them out for us. So what we're going to do is look at the mean bug application. If we attempt to log into it with just username admin, password admin, it doesn't work. But what we're going to do is we're actually going to intercept this authentication request using Burp Suite proxy, and then we're going to change the password value to our payload $ne equals null. And then we're going to forward that request on to the application, and we see that we're able to authenticate without actually providing a valid password. So if we navigate into the application, we see we can also query some invoices and do some other interesting things. So we're going to attempt the same attack here. So what we're going to do is we're going to intercept the request. And if we notice, this is not a simple post form. This is a more complex form, uses a JSON body. So what we're going to do is we're going to change the content type to form URL encoded. And then we're simply going to change our payload to the URL encoded payload containing value ne equals null. And what it's going to do is it's going to return all the entries in our database, just like so. So the way we're going to fix this is we're going to go to our authentication find once query, and we're going to cast our user variable to a string, and we're going to cast our password variable to a string, so that it's no longer acting as that query operator, but query selector operator, but rather as a string representation. So we restart our server, and we're going to do the same attack as before. So we're going to intercept the request. We're going to submit the request. We're going to alter it, again, with password $ne null. And we're going to forward that onto the application. And you see now the injection attack no longer works. So again, basically for Express to parse this out, we need to use a URL encoded payload either in the GET request or in the simple post request. But even if we don't have that, we can still change the content type and instead change our body as well, so that we're sending that URL encoded request, and we're actually able to exploit non-simple post forms as well. So continuing with MongoDB, one of the other issues is insecure configuration. So by default, MongoDB does not have authentication. It's disabled. There was a CSO online article back in January detailing how more than 40,000 MongoDB instances were compromised by ransomware because they were publicly exposed to the internet with no authentication. Not a good combination. The Shadow Server project is another interesting project that does periodic queries of the entire IPv4 space looking for MongoDB instances without authentication. And as of just a few days ago, there were still almost 28,000 instances, again, publicly exposed with no authentication. So that presents a problem, but it gets worse. So if you're using an older version of MongoDB, not only does it have no authentication by default, you're also going to be binding to all interfaces by default. So again, you have an out-of-the-box database server that, as soon as you stand it up, it's going to be publicly exposed and have no authentication. Some other configuration issues with MongoDB, they provide the option to enable an HTTP and REST interface. Now, these guys aren't enabled by default, but if they have been enabled, it's going to present some information leakage issues. So they're configured in the etc MongoDB configuration file, and there's simply two options that can be turned on or off. And how do we fix these? Well, first, we need to make sure that we're configuring bind IP to only bind to our necessary interfaces. Turn on authentication and turn off HTTP interface and REST options. So we'll look at an example MongoDB instance that's insecurely configured and show how these poor options can be exploited. So we're going to navigate to our MongoDB instance, and by default, the REST interface is exposed on port 28017. So when you navigate to it, we have these various commands up top that are our REST interfaces, and we can do things like get build information on the database instance, show the databases. And then we can also scroll down and look at the various logs for this MongoDB instance. So lots of good information that we can glean as an attacker if we can gain access to this. Again, because authentication is disabled, we can connect directly to our database using the Mongo shell utility and query it directly and get things like user credentials. So how do we fix this? Well, we're going to go to the MongoDB configuration file, and the first thing we're going to do is turn on authentication. Next, if we don't want to bind to all interfaces, then we need to specify which interface we're going to bind to. And then we need to turn off the HTTP interface and REST interface options. So now we're going to restart our MongoDB instance. And we're going to connect to it again. And once we connect to it, we see that when we try to do the same find query, we don't get anything. We're unauthorized. And if we try to access the HTTP interface, again, it's not being served anymore. All right, enough with MongoDB. Let's look at Express. So Express is the server component of our mean stack. And Express is a concept of routes and middleware. Okay, so we can define various routes. We can define various middleware components and apply that middleware to those routes. But our middleware, if it's applied globally, so we're saying, hey, apply this to all the routes in our Express stack, that middleware is only going to be applied to routes that are lower down in our Express stack, so routes that have been defined after that middleware. So this can present a problem if we have sensitive routes that are defined before our middleware that performs some sort of security function, right? So we have the middleware is logged in. This is our authentication middleware that checks to see, is this user actually authenticated for this resource that they're requesting? So we have two routes. First is the secure add invoice route. So this lets us add an invoice to our application, and it's defined after this middleware, so it's going to be protected. We have to be authenticated before we can access this. The other route, remove invoice, is defined before this middleware. So the problem here is even though we're applying this middleware globally, it's being applied after this other route, and it's not actually going to protect it. So the remediation here is simply to check the order of our routes and our middleware. And where this becomes a more prominent issue is when we're dealing with an older application, something that we're performing maintenance on, adding routes to it. Before we just drop a route into the stack, we have to look at all the other middleware and make sure that we're not defining this route before some sort of middleware that needs to be protecting it. All right, continuing with Express, case-insensitive routing. So by default, Express uses case-insensitive routing, meaning that capital secure managed invoices is going to be the same as lowercase secure managed invoices. Well, this becomes a problem if our middleware is applied based on that route path. So we have our authentication middleware, and we're applying it to all routes that begin with the path /secure. But the regex we're using is case insensitive, so it's only looking for routes that begin with /lowercase secure. And we have in our application, the only route that is defined is /lowercase secure. Well, this becomes a problem if we're using case-insensitive routing, which Express does by default, because capital secure is going to return the same resource, but it's not going to be protected by this middleware. So how do we fix this? Well, we have two options. We can either design our application around these case-insensitive routes. In this example, we would need to change this regular expression to a case-insensitive regular expression, or we can tell Express, hey, only use case-sensitive routes. And we can do that by setting the case-sensitive routing option to true, in which case the Express server will no longer return the same resource for capital secure managed invoices as it does for lowercase secure managed invoices. So let's look at an example. If we try to force browse to lowercase secure managed invoices, we see that we're unable to do so. It rejects our request and sends us back to the login screen. However, if we change this to capital secure managed invoices, then we can actually force browse to an authenticated page. And again, this is because Express is using this case-insensitive routes. So we have two options to fix this. We can either, again, go in and set this regular expression as case-insensitive so that it's applying to lowercase secure or uppercase secure, or we can set the case-sensitive routing option to true for Express to tell it to use only case-sensitive routes. So that's what we're going to do in this case. We're going to restart our server. And we're going to try the same forced browsing attempt again. And you see that this time, it doesn't return the resource. It says the capital secure manage invoices doesn't exist. All right, continuing with Express, CSRF and GET request. So CSRF is a popular anti-CSRF middleware for Express. It has 1.2 million downloads as of March, and the link to that package is located in the slide. And basically what this middleware does is it provides the server-side checking of our anti-CSRF token, right? So it looks for the inbound request on the route, it parses out the CSRF token and checks to make sure that it's actually a valid request coming from one of our pages rather than a CSRF attack. But the problem is if we apply this middleware globally, so we're telling Express to apply to all routes, it's not going to get applied to any route that uses the GET method. So if you look at our example here, it's going to be applied to secure add invoice, but not to secure remove invoice. Again, because the secure remove invoice is using the GET method. So how do we fix this? Well, the recommended remediation in the most appropriate order is first to avoid state changing requests with the GET method. So anything that changes state on our server, it's generally bad hygiene to perform those requests with the GET method. So as we can see in the excerpt here, we've simply changed this to a post request, to a route expecting the post method. And in this case, it's going to be properly protected by our CSRF middleware. The other option is to remove the GET method from the ignore methods option. So again, with the CSRF middleware, we can define the ignore methods option as only head and options. We've removed GET from that array, and it's going to tell the middleware, no longer ignore the GET method. Go ahead and apply yourself to routes that use the GET method. And the final option is to simply apply our middleware per route rather than globally. So previously we were applying it to the entire application stack. Well, we can also apply it to each individual route by manually inserting into that route definition. Now, this is the least recommended option, primarily because it increases the likelihood that a developer is going to forget to include it on a sensitive route. But it is a viable option. So we'll look at an example. Again, we're logged into our mean-bug application, and we see that we can navigate over to the invoice page. And if we look at our database of invoices, we see that it contains two invoices, ID 3 and ID 4. So what we're going to do is click on this link. This represents a malicious link sent to us by an attacker that sends a request to remove invoice route for ID 000004. And by simply clicking on that link, we've deleted that invoice. If we go back and look at the database, query it again, we see that number 4 has been removed, only 3 remain. So that's a prime example of our CSRF attack. How do we fix it? Well, we can change that GET request to a post request, or a post route, or we can go to the CSRF middleware definition here and change the ignore options method to only include head and options. So that's what we've done in this case. We've told the middleware, hey, apply yourself to the GET routes as well. We've restarted our server, and now we'll perform the same attack again. So we'll create a new URL. Again, it's going to our mean-bug application for remove invoice with the value. This time we'll use 000003, and we'll simulate the attack again. So when we click on that link, instead of removing the actual invoice, we see we get a form tampered with message. So our CSRF protection is now being applied to that route appropriately. And if we look at the database of our invoices, we see that our invoice is still there. So we've prevented that cross-site request forgery attack. All right, continuing with Express, session revocation and JWTs. So JWTs, or JSON Web Tokens, are becoming more and more popular as a means to store our users' session data client-side. So the way this works, the data is digitally signed. Our JWT has a header, it has our body, which has the actual data for that user's session, and then it has a signature. So the signature is what validates that this JWT hasn't been tampered with. And that signature is going to be checked server-side to make sure that, again, that no tampering has occurred. So the big advantage here is our server no longer needs to maintain session state data server-side. We can push that over to the client, right? And because this JWT is signed, we can have a level of assurance that this JWT hasn't actually been tampered with. But this also means that the application cannot revoke our session. So even if we set the expires in or max age attribute on the session cookie, all we're doing is requesting that the browser purge the session after that set amount of time. We're not actually invalidating the session. So if all we're relying on is expires in or maxed age, this session will last forever. It can be replayed indefinitely, days, weeks, months down the road, and the server doesn't know any better. So the other problem here is the user can't log out of their session. So if the user programmatically logs out of our application, all it's going to do is simply redirect them to the login page. It could potentially purge the session from the browser, but that session is still going to be valid. If it's been captured, it can be replayed even though our user has, quote, logged out. So how do we fix this? Well, our JWTs have to maintain an internal expiration value. So what that means is inside that body of our JWT, remember that data is signed, it can't be tampered with, we have to maintain an expiration value that the server will check to see if this JWT is still valid or if it's been expired. One package that's fairly common that does this for us is client sessions. Again, we can use this off-the-shelf package to implement this functionality for us in our Express stack. Another consideration is generally we want to make this JWT session time a little bit shorter than what we would use with conventional sessions. And again, that's because our user can't log out of a session that's persisted with JWTs. So the only way that session is going to actually be terminated is for that internal value to expire. So again, this is using the client sessions package. It has this internal duration option where we can set that internal duration of this JWT, and also this max age where we can set the max age of the cookie. From a security perspective, the max age doesn't mean anything, because again, we're just requesting that the browser purge that session. It's not actually invalidating it. So the duration is what we're really concerned about when we're looking at this. All right, so to demonstrate this, we've authenticated to our application, we've logged into our session, and this first value is the time that our JWT session token was created, and that second value is how long it's going to be valid. And these are in milliseconds. So we're going to log out of the application, and we see we're redirected to the login page. And if we look at our session, the session has been purged from our browser. It's now set to null. But if we go into our HTTP proxy, we've captured the session value, this JWT, we can replay it and it's still going to be valid, right? It's going to continue to be valid until that internal expiration time expires. So JWTs, they're cool, but they have some interesting quirks from a security perspective that we need to be aware of. All right, so enough with Express. Next we're going to talk about Angular. Specifically expression injection. So Angular templates are defined by our ng app directive, which is bound to our body HTML element in this example. And then the expressions are denoted by our double curly braces. In this case, the double curly braces are calling the variable user. So one of the problems or the causes of our Angular expression injection is curly braces are not encoded by off-the-shelf HTML encoding solutions. So what that means is even if we're encoding our untrusted input for use within an HTML context, our Angular expression injection may still be possible because we're not actually encoding those curly braces. And those curly braces are the control characters that are used to denote our Angular expression. So injecting curly braces also means an attacker can evaluate arbitrary expressions. And expressions are not sandboxed as of Angular 1.6. So what that means is we're not confined to the Angular scope object. We can access other, basically anything that we'd like by not having to worry about that sandbox. And even if we're using an older version, sandbox escaping payloads still exist for previous versions. So what does this look like? So our malicious Angular code is injected through our untrusted input. Even if we're passing it through some sort of HTML encoding solution, only our HTML special characters are encoded. So our Angular curly braces are not going to be encoded. And they're going to be written to our Angular template. Our Angular template is then passed over to our Angular expression engine, which is going to render those expressions, including our malicious code that has been inserted by our attacker, and then it's going to execute within the view. Now, this can all occur client-side, or it can occur server-side if we're using things like Jade, EJS, Pug, some of the server-side templates to create our Angular template and then sending it to the client like so. So how do we fix this? Well, one of the options is to reduce the scope of the ng-app directive. So instead of binding to the body, we can bind to a specific div or table element or some sort of element that's has a smaller scope. And if we're not writing untrusted input to that element before it's being sent to our Angular template engine, then we can't inject anything, right? Because the template engine is only going to be looking at that limited scope. The other option is to use the ng non-bindable directive. This attribute, if we add it to our HTML element, is going to tell the Angular expression engine, hey, don't render this. This is not part of the actual template. And the third option is to sanitize our untrusted input to remove curly braces. Again, because our HTML solutions aren't going to do this for us, it generally means we have to use some sort of custom implemented solution to remove those curly braces from our untrusted input. So as an example, if we log into our application with invalid credentials, we see that they're reflected back onto the page for us. So if we try a conventional script alert 1 attack, we see that it's unsuccessful. In this instance, it's actually being written to a text node, and it's not within an HTML context. But if we inject our Angular expression 1+1, it renders to 2. So we know we have expression injection. So we're going to use the constructor.constructor to call alert. We'll inject that into insert that into our username field, submit it, and we see that we have successful cross-site scripting using Angular expression injection. So how do we fix this? Well, one option, again, is to limit the scope of the ng-app directive. If we go down here, this is where our untrusted input is actually being written into our HTML. And this is where it's grabbing that untrusted input from the URI and inserting it into that text node. So all we're going to do is, in this paragraph element, we're going to insert the ng non-bindable directive. So again, we're telling the Angular expression engine, don't treat this as an Angular template, ignore it. So when we execute the same attack again, we see that instead of expression injection, our untrusted input is safely written to the page. Again, because we told the Angular expression engine, ignore this part of the template. All right, next, local storage information leakage, again, dealing with Angular. So one of the things that HTML5 gave us was additional storage options client-side. Right? So instead of just storing stuff in cookies, we can now store stuff in local storage and session storage. So the key difference between the two is local storage persists indefinitely unless we explicitly clear it, whereas session storage only persists as long as that browser session is active. So if we close our browser window, session storage is automatically cleared for us. From a security perspective, though, that presents some problems, primarily because if we go to our, if we log out, leave our application, close the window, and then open it back up, if we're storing data in local storage, we can go and inspect that local storage and see whatever data was there previously, whether it was from a previous user. And if we're putting anything of sensitive nature in there, then that can potentially be exposed. So most Angular services use the less secure local storage by default. These are three common ones. Angular Storage uses local storage by default. Angular Locker uses local storage by default. And ng Storage, it actually doesn't define one or the other. So it's up to the developer to actually choose which one that they want to use. But none of these use the more secure session storage by default. You say, so what? I clear local storage on logout. Well, we can't necessarily rely on the user to programmatically log out of our application. If they just close that window and we have sensitive data that's being stored in local storage, it's going to persist there indefinitely. So how do we fix this? Well, we need to ask ourselves, does the application really need to store sensitive data in web storage? If not, we shouldn't do it, because remember, anything client-side is inherently untrusted. If we decide, yeah, we really do need to store this data client-side, then we need to configure the service to use session storage. This example uses the Angular storage module, and you can see we're going, accessing the store provider set store method, and just changing that from local storage to session storage. So now the application will use session storage rather than local storage. And even once we set this to use session storage, we still need to programmatically clear our session storage on logout, right? Because if the user logs out of the application and then navigates to some other page, does whatever else, that data is still going to sit there in session storage if we didn't programmatically clear it on logout. So even though it's cleared once the window is closed, we still want to programmatically clear it. All right, continuing with Angular, bypassing the strict contextual escaping service. So Angular provides the SCE service, which sanitizes malicious or commonly abused HTML tags, attributes, protocols, and so forth. So it's going to remove things like script tags, on-error attributes, on-mouse over, the JavaScript protocol, so forth and so on. So the strict contextual escaping service is a good thing, but it can be disabled. You can disable it per instance by calling the trust as HTML, trust as CSS, trust as URI, or the shorter version, just trust as, and then specifying what you want to trust it as. So again, this is per instance of whatever this data is. We're saying trust this specific piece of data. It can also be disabled globally, and there's really no reason why you would ever do this in production, right? If we set the SCE provider enabled to false, then we're telling Angular, don't do any strict contextual escaping. And again, there's no reason why we'd want to do that globally globally across our whole application. So we'll look at an example, again, with our mean bug application. If we query an invalid invoice ID, we see that it's reflected back onto the page. So what we're going to do is insert this image tag where the source is X, which is going to not evaluate anything, and where the on-error attribute is an alert message. But we see it didn't actually work, right? All we got was the empty image tag. So if we inspect this actual HTML element, then we see that all we have is image source equals X. Our on-error alert attribute has been stripped from that element. So if we go into our Angular application code, you see we're using the SCE service here. We're going to disable the SCE service globally. We're going to reload our Angular page. And then we're going to submit the same payload again. And this time when we submit it, the cross-site scripting attack is successful. And if we look at the HTML, we see that we see that our on-error attribute is still there, right? We've disabled our strict contextual escaping service, and it's no longer sanitizing these commonly abused attributes, scripts, and script tags and protocols. So finally, Node.js. So Node.js is our server-side JavaScript environment that lets us run this technology stack. So with Node.js, it requires root privileges to bind to any port lower than 1000. So if we're spinning up our application server on port 80, port 443, we've got to use sudo to our root account or use an account with elevated privileges to do so, which is generally not a good idea, right? We generally don't want our web app server running as root because in the event of a compromise, our impact is going to be much higher, right? If an attacker can compromise that account that we're running under, then they can do a lot more. So what we need to do is go ahead and use these elevated privileges to bind to these low ports, and then once we start our server, once we do the binding, then drop down to a less privileged account using process set user ID and process set group ID. And then another quirk with Node.js is by default it runs in development mode. So Node.js has a node environmental or node env variable that lets us set the environment that we're running in. So by default it runs in development mode, and if Express is running on top of Node.js, it looks at this node env variable to determine how it's going to react in certain scenarios, right? One of those being if it gets an uncaught error. So if Express encounters an uncaught error and it's running on Node.js in development mode, then it returns that whole error back to the user. So that error can include things like file paths, stack traces, other sensitive information that we probably don't want to disclose. So how do we fix this? Well, when we run our Node.js, we want to set the node env variable to something other than development. So we can set it to production. Really, any string or any value other than development is going to prevent this, right? So in this solution, we've set the node env variable to production on the command line when we start our Express server in our node environment. And you can see that now when we request a resource that doesn't exist, instead of passing the uncaught error back to the user, it simply returns a more benign not found. And that is a very quick walk through the mean stack and some common mistakes and vulnerabilities that you may encounter. That's it for this talk. Are there any questions?
Thank you very much, Stuart. Sorry, questions?
Hello. Sorry if this is an obvious answer, but at the start when you were chatting about not using get to delete things and you switched to using post,
yes,
was there a reason why you didn't use the delete verb for that?
So in that situation, we weren't actually deleting a resource on the server. We were hitting an API that was then querying our database and removing that invoice from the database.
Yeah, but you could still have used the HTTP delete verb on your REST API, though.
Yeah, so we could use other verbs. They don't have to use the post method, right? The point there was simply if we can avoid changing state with GET requests, right? Then we should do so because that's considered poor hygiene.
Well, that's
right.
I just wanted to check there wasn't some reason that I didn't know.
No. And if we were using delete, then the CSRF middleware would be applied to it appropriately. We just want to avoid using GET for those state changing
Good. Thank you.
resources.
Anyone else? Sorry. Any other questions? Okay, folks, well then that's it. If I could ask you again, just to remind you, please, if you would, put one of the tickets in on your way out. Just to as feedback for ourselves. And again, thanks very much, David.
Thank you.